Hello friends, welcome to video lecture on dynamics of machinery. In today's lecture, we'll learn about methods for formulation of differential equations. So already we know the different steps for vibration analysis. So first step as per our earlier discussion is mathematical modeling of any physical system. Then formulation of governing equation or differential equations. Then solution of differential equation. Then next one, interpretation of result. So as per second step, formulation of differential equation. So different methods are there. We'll just see the different methods. Okay. So methods for formulation of differential equations. So the basic methods are: first one, equilibrium method or free body diagram method, and second one, method based on law of conservation of energy. Again, the equilibrium method or the free body diagram method is classified into two different sub-methods. First one, method based on Newton's second law of motion, and second one, method based on D'Alembert's principle. So the second case, this one, method based on law of conservation of energy, we'll see in the next lecture. Okay. Now see the Newton's second law of motion for the development of differential equation. Now let us start with the first method, Newton's second law of motion or method based upon Newton's second law of motion. The differential equation of the motion can be developed by using Newton's second law of motion on the free body diagram of the system. This method states that the accelerating force due to the mass should be equal to sum of external forces in the given system. So as we know, Newton's second law of motion. So what's about the mathematical statement for this one? We know F equals to ma, like this one. So what's about the meaning for this one? M is nothing but the mass. So what's about the A indicate the acceleration. Okay. So as per our earlier notations we have used for the acceleration, can I write this one in this way? Mx, mx double dot. This double dot you're just writing for the this one double dot for the acceleration. Okay. So what's about this one? This indicate the accelerating force. Accelerating force equals to, so what's about this force? I'll write this force here like this one. So this force we can indicate like this one, summation of all the external forces. Now this becomes easy for us to read. Okay. So what's about our earlier statement regarding this Newton's second law of motion? So this indicate, this method states that accelerating force due to mass should be equal to summation of external forces. That's it, a simple statement for this one. Okay. So how we can develop the relation for uh, natural frequency of the given system. Okay. For that, let us consider the spring mass system. Okay. For that, I'll just draw here. Now if you look towards figure number A, figure number B, and figure number C, okay, so what's about this one? A simple spring we are considered here, okay. So the stiffness for this spring, okay, like this one. If I attach some mass at the end of this spring, then the static deflection of that spring takes place by this distance, okay, delta st. So what's about this one? What's about the spring force come here, okay, k into delta st, okay. So how this one k into delta st will come? What's about the basic definition for the stiffness? Stiffness is nothing but the force per unit displacement. I'll just write it here, okay. Since we know k is nothing but the force per unit displacement, okay. So in the same way, if I take this one x here, so what we get here? Displacement multiplied by k equals to force. This force is nothing but the spring force. So that's why this one k into delta st is written here. So delta st is nothing but the static deflection of the spring because of application of this mass, okay. So what's about next one? So this is nothing but the its main position, okay. When I pull this mass, okay, in downward direction like this one, then what will happen then? So what's about this one? The previous displacement of this one with us, how much? This one with us delta st. So because of disturbance given in the system or pulling of this mass in downward direction, okay. So I'll just show that mass here, okay, so that this one clear to you. Now observe this distance, okay. This distance with us x plus delta st, okay. Now what's about this total displacement? X plus delta st, like this. So what's about the spring force here? Spring force is nothing but here in this case the multiplication of displacement and the stiffness of that spring, okay. So x plus delta st will come here. So I'll write here the information regarding this free spring, okay. So what's about this one? This is nothing but the free spring with the mass. Free spring with mass, okay. And what's about the third case? Spring and mass subjected to disturbance. Now, as per our previous discussion regarding the stiffness of the spring, okay, what's about the stiffness? Stiffness is nothing but, what's about the relation we are discussing regarding the stiffness? It is nothing but the applied force divided by displacement done. So in this case, just give the figure here. So whatever the weight of this one, that will adds in the downward direction, okay. So this force must be, okay, weight, okay, in terms of this one. So weight, I'll just write here mg. So displacement with us static deflection, that is delta st, okay. Write this like this one. To the relation number 1 for this one. Now next one, let the spring and mass system is subjected. So initially the spring is here, after that some mass is attached, okay. Self weight of this one is nothing but the mg. Because of this one the static deflection comes in the system is delta st. Now when the disturbance is given for this system, the mass will move in a downward direction again by this distance x, okay. So initial displacement with us delta st, next displacement with us x, so total displacement with us x plus delta st. So spring force we can get like this one, k into x plus delta st. Now I'll draw the free body diagram of this given system at this instant. Okay, so for that, see, the various forces are acting on this mass attached here. Okay, for that I'll separate this mass like this. So whatever the spring, okay, available with us, if I pull this mass into downward direction, what will happen? The spring resists the motion of this mass in downward direction. So what's about this one? The spring force will opposes that motion. Okay, the tendency of this mass to move in downward direction. So opposite force, okay, comes because of this one spring. Okay, so what's about this one? The direction of the spring must be come in upward direction like this one. So the tendency of this mass, we are just pulling this mass in downward direction, so the displacement direction must be towards a downward direction. At the same time, the acceleration direction is also in downward direction. So what's about the accelerating force? Okay, so accelerating force, the direction for this one also in downward direction, whose magnitude with us mx double dot. Okay, so what's about the self weight of this one? Already I have seen mg is nothing but the self weight. Okay, so what's about this force and this force? These two forces are nothing but the external forces. External forces. And what's about this one? This is nothing but the accelerating force. Now what's about this one? This indicates the free body diagram of the given spring mass system. Okay, so these two forces, this force, spring force, and the self weight of that block are nothing but the external forces. Okay, so what's about this one? This is nothing but the direction of displacement. And what's about this one? The acceleration will comes in the same direction. So what's about this one? This indicates the accelerating force. Okay, and these two forces are external forces. Okay, so as per Newton's law of motion, okay, so what's about that law? Accelerating force equals to summation of external forces. Okay, so here some of the sign conventions are there. Okay, so we'll just see that sign conventions. Conventions used in free body diagram. Okay, so what's about that conventions? So if any downward force is there, then you have to consider the positive sign for the same. Okay, if any force is in upward direction, then you have to consider the negative sign for the same. Okay, if any anti-clockwise movement is there, then you have to consider the positive sign for the same. And if the clockwise moment available in the system, then you have to consider the negative sign for the same. Okay, now for the spring mass system, already the forces in front of you from this free body diagram. Okay, Now see the direction of every force available in front of you. What's about the direction of this accelerating force in downward direction? So as per sign conventions we have used here, for the downward you have to consider the positive sign. Okay, and then what's about this one? This is nothing but the self weight. For this also you have to consider the plus sign. Okay, so what's about this one? This is nothing but the spring force. This force acts in upward direction. So as per sign conventions we have used here, the sign for the spring force must be negative. Okay, so as per Newton's second law of motion, try to write the equation here with the help of these various forces. So first of all, if you just look towards the left side of this Newton's second law of motion, this is the accelerating force. Okay, so only single accelerating force with us here. So accelerating force is mx double dot equals to what's about the next one? Summation of external forces. Now concentrate on this one, this force mg. Okay, I'll just write some conventions here. Okay, beside in every actually force, so that you can get the clearly information regarding this one. I'll show intentionally here downward direction, so that the positive sign should be given for this force. Here the positive sign should be given for this force. So next force with us, okay, this force is here, so negative sign must be given for this spring force. Okay, like this. Okay, now try to solve this one. Mx double dot equals to, what's about this force? This force, I'll just write this force as it is, mg minus multiply by this k term to inside term, like this one, minus kx minus k into delta st will come. Okay, so the next step, after simplification, okay, just say the next step, mx double dot equals to mg minus kx minus k into delta st. Okay, now if you concentrate on this term and this term, okay, since the weight or self weight of this block, okay, must be equals to the spring force here occurred because of the static deflection. Okay, both these terms balance with each other, so this term and this term get cancelled. So you can get this relation like this one, mx double dot equals to minus k into x, like this one. What's about the relation we get here? Mx double dot plus kx must be equals to 0 in this way. Now I'll just write this relation like this one, give equation number next for this one, equation number 2. Okay, so I'll write this relation like this one, x double dot plus k by m into x equals to 0. Okay, so giving equation number 2 here, I'll just give the equation number 2 here. Okay, now compare this equation with the SHM. Comparing this equation with simple harmonic motion. So we know x double dot plus omega square x as per our previous discussion. Okay, equation number 3 for this one. Just compare equation number 2 and equation number 3. What do we get here? We can get omega square equals to k divided by m. Okay, so in this analysis damping is not considered, hence omega, which is the resulting frequency due to disturbance, okay, represents the natural frequency of the given system. So I'll write this one in this way, omega n equals to square root of k divided by m. Okay, like this, equation number 3 for this. Also we know what's about the meaning of time period. So time period t is nothing but 2 pi divided by omega. So what we get here regarding the time period t? T equals to 2 pi, see omega n, this omega term is in denominator, okay? So we can get this term like this one, m divided by k, like this, okay? So give equation number 4 for this. Now we know the frequency in terms of hertz, okay? So frequency in terms of hertz is nothing but it is the reciprocal of time period, okay? So the frequency in hertz will be Fn equals to 1 upon t, okay? So if I take the reciprocal of this one, what do you get here? 1 upon 2 pi square root of k divided by m, okay? This is the relation for frequency in terms of hertz, okay? So it is observed that the natural frequency in the present case is independent of the gravitational force, as it is neutralized by the spring force due to static deflection term, okay? So in one of the step we have seen this one mg, okay, must be equals to k into delta st, okay? In one of the step already we have seen, okay? Now in such cases, okay, it is correct to neglect both the self weight as well as this one static deflection, okay? This is about the Newton's second law of motion, or method based upon the Newton's second law of motion. So let us discuss a next method, okay? Method based on the D'Alembert's principle, okay? So in this case, this method is based upon the fact that whenever a system is in equilibrium, the algebraic sum of forces and moment on it must be zero, okay? So D'Alembert's principle converts the dynamic problem into static problem by adding the inertia force, okay? So consider the free body diagram. So in Newton's second law of motion, okay, so already I have seen the spring mass system, okay, like in this one spring, okay? If I pull this one mass in downward direction, okay, so whatever the deflection of the spring, okay, comes, and because of that, so whatever the forces are arised here, already we have drawn here free body diagram, okay? So by using the same diagram, we'll just continue our discussion, okay? So what's about this one? This indicate the spring force, this indicate the what's about this one? This is nothing but the self weight, okay? So what's about this one? What's about this one? So whenever we pull that mass into downward direction, this is nothing but the direction for which one? The displacement, as well as what's about this indicate the acceleration direction, okay? Now as per D'Alembert's principle, what's about the D'Alembert's principle? Here the summation of inertia force or forces plus summation of external forces must be equals to 0, okay? So in this case, whatever the moment of this one we have considered in the downward direction, okay, downward direction. So what's about this one? Inertia force will opposes the motion of this one in downward direction, and you have to show the direction of this one inertia force in upward direction. So as per this D'Alembert's principle, inertia forces, summation of inertia forces plus summation of external forces equals to 0. So as per our discussion, these two forces indicate the external forces, and this is nothing but the inertia force. Now the various notations already have seen. So what's about the sign for this one? The minus sign must given for this one. Okay. So what's about this one? For the downward force, you have to give as plus sign. Okay. So what's about the external force? External force, this one in upward direction. So this is nothing but the spring force. You have to give the minus sign for this spring force also. Okay. Now rearrange various terms. Minus this one k into x minus k into delta st must be equals to 0. Okay. Now simplify this one. Here mx double dot equals to, take some of the terms towards the another side of this one. I'll just keep this one accelerating term or inertia force term towards the left side. If I consider the minus sign for the plus sign for this one, then the signs for the other forces, if I take towards the another side, okay, that will remains as it is into delta st. So as per our previous discussion, so what's about this one? Mg, since Mg equals to k into delta st, what's about the meaning for this one? Nothing but the self weight of the given block must be equivalent with the static deflection of the given spring, okay, or spring force because of the static deflection. So this term and this term get cancelled. Get this one mx double dot plus kx must be equals to 0. So what's about the next one? If I write this one, this form, okay, what's about this one? Equation number A for this. If we compare with the SHM equation, we know the SHM equation, x double dot plus omega square, okay, into x equals to 0. Equating both the equation, what we get, can get the same result, okay, root of k divided by m. And further, so what's about this square root of k by m? Okay, so you can get the frequency. This is nothing but the circular frequency of given system, okay, and we can get a frequency in terms of hertz by this relation k by m. We compare this with the earlier result, get the same result.